Last time we proved this big theorem that over principal ideal domains, if we have a submodule of a finite free module, then we can choose aligned bases in both modules. So that we have a basis in M prime, and basis elements are scalar multiples of certain basis elements of M. And this lecture will be about deriving a lot of corollaries from this theorem. So for the first corollary, I would like to remind you the notion of torsion elements. So a quick reminder, if M is an R module, then we define the set of torsion elements in M as those elements for which there exists a non-zero scalar x in R, such that x times M is equal to 0. And we saw that if R is an integral domain, then tors of M is a submodule and not just a subset. And we say that an R module R is called a torsion module. Sorry. An R module M is a torsion module if all elements of M are torsion elements. So if tors M is equal to M. And the first corollary of this theorem is that if we have two R modules, submodule of a finitely generated free module, and R is a principal ideal domain, in this case, rank of M prime coincides with rank of M precisely when M mod M prime is a torsion module. The proof of this corollary is a direct application of theorem about aligned bases. So let's say that N is the rank of M and K is the rank of M prime. Then we can choose aligned bases. So V1 through Vn spans M, and A1 V1 through a k vk spans m prime. And let us study the quotient m mod m prime. M mod m prime. Notice that since we have a basis, we can write m as a direct sum of three modules of rank 1. So rv1 plus rv2 plus etc. plus rvn. And similarly, we can write m prime as a direct sum of rank 1 free modules, ra1 b1 plus etc. plus rak vk. And so we can notice, because the bases are aligned, we can in fact split this quotient into a direct sum of quotients, and we get rv1 mod ra1 v1 plus etc. through k vk mod rak vk plus, and then the rest of the summands get quotiented out by the zero modules. So we get just r vk plus 1 plus etc. plus rvn. And let's see. So this module is a torsion module in this representation, if and only if it does not have any free part. So m mod m prime is torsion if and only if this free part is 0, so that k is equal to m. Because this part consists only of torsion modules. So in this module, any element multiplied by a1 will be equal to 0. And similarly for this module. And so m mod m prime is torsion if and only if k is equal to n, but these are exactly the ranks of these modules. Rank m prime is equal to rank m. And this concludes the proof. Now I will formulate a lemma that if R is a principal ideal domain and M is a finitely generated R module, then M is isomorphic to a direct sum of some finite free R module and a torsion module, which is tors of M. And you can probably already see how I'm going to prove it. We know that tors of M is a submodule of M because R is in particular an integral domain. And so we can form the quotient module M mod tors M. And this module M mod tors M, first it is finitely generated, because if M was finitely generated, then images of its generators in the quotient will generate the quotient module. So M mod tors M is finitely generated, and moreover it is torsion free, because we quotiented out all the torsion. And therefore, since we are working over PIDs, it is a free module. And finitely generated. And now, since we have a surjection onto a free module, we know that we have a section, sigma, so that if pi is the surjection, then the composition of the section with pi is the identity homomorphism of the quotient module. I will just write ID here. And so the surjection splits, and we have that M is isomorphic to the kernel of this surjection, towards M. Direct sum with the image of this surjection. And this is what we proved. So this is the torsion part, and the finite free part is this quotient module. And now the theorem that I advertised just a lot when we just started when we just started talking about modules. Theorem on the structure of finitely generated modules over principal ideal domains. Which says that if R is a principal ideal domain and M is a finitely generated R module, then M has the form of some finite free part, finite free, direct sum with the big direct sum, still finite, for I going from 1 to some M capital, of cyclic torsion modules are mod out by Pi to the Ki. Where Pi in R are prime elements and Ki's are integer numbers. And note that Pi's can repeat. So for example, P1 can be equal to P10. And onto the proof. Note that by lemma, M is isomorphic to some finite free module plus the torsion part. Where F is finite free and T is torsion, tors of M. And so now I want to say that the torsion module can be decomposed as a sum of cyclic modules. So T is finitely generated. again by my remark in the proof of the lemma. So I can pick generators x1, comma, dot, 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 xm in T. And these generators define a surjection from R to the M onto T. And this surjective homomorphism sends ith standard basis vector to the generator xi. And let me call this surjection pi. So we know by the first isomorphism theorem that T is isomorphic to Rm mod the kernel of pi. And if I denote the kernel of pi by k, it is a submodule of a finite free module. Therefore, it is also free, and I can talk about its rank. And moreover, we know that Rm mod k is torsion, which means by this corollary that k is in fact a free module of the same rank as Rm. So k is free of rank m by the corollary. Okay, and we spent a lot of time proving a theorem about aligned bases, so let me use it now. So we want to pick aligned bases for k and Rm. So let's say that Rm has the basis v1, comma, dot, 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 vm, and k has basis a1, v1, dot, 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 am, vm. Because, so here m is the same because k is the same rank as Rm. And so we can write that T is isomorphic to Rm mod k, and this is in turn isomorphic due to the aligned basis theorem. It is isomorphic to R v1 over Ra1 v1 direct sum dot, 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 Rvm Ram Vm. And I can just write it as using the direct sum notation, sum over I from 1 to m of R mod out by the ideal generated by A1. I'm just rewriting how, AI. I'm just rewriting how these summands look like if we identify RV1 with R by sending 1 to V1. And this is already almost the expression that we want to get here, but I want to refine this decomposition further by using the Chinese remainder theorem. So if if we view R mod AI as a module, as a ring, then we can apply Chinese remainder theorem. So we write A1 as a AI as a product of some prime element PI1 to the power Li1 times Pi Ri to the power Li. So really I'm writing a prime decomposition of AI so that each factor here is co-prime with every other factor. So that Pij's is co-prime with Pij prime for any j and j prime. And by Chinese remainder theorem, R mod AI is isomorphic as a ring to R mod Pi1 Li1 product with R mod Pi some index R Lir. But being a ring isomorphism is a stronger condition than being an R module homomorphism, an R module isomorphism. So, in particular, we have that this is an isomorphism of R modules, and we know that finite direct products are the same as finite direct sums. So, for modules, we have an isomorphism R mod AI and this big direct sum Pi1 to the power Li1 direct sum R mod Pir to the power Lir. And this is how we further decompose this direct sum into direct sum of cyclic modules, where we mod out by powers of prime elements. And as I said, because we may have many summons of the form R mod AI, and AIs are not necessarily co-prime, and that is how we may get repeating prime elements here in this big sum. And I just want to mention that by doing some more work, you can prove a uniqueness result on this decomposition. So, for example, you can see immediately that this finite free module has fixed rank because it is in fact uniquely determined by M, because it is M quotient out by the torsion. But also you can formulate, or you can read that you can formulate a similar uniqueness result for this part, so that after permuting factors and multiplying by units, this part would also be unique. But I'm not going to prove it, and instead I would like to focus on very exciting corollaries of this structure theorem. So, particular case number 1, I will formulate it as a corollary number 1, It is structure of finitely generated abelian groups. So if M is a finitely generated abelian group, then I can consider M as a Z module, and now I am restating or basically rewriting the result of this theorem for Z modules. Then M is isomorphic to Z to the power N plus a direct sum of cyclic abelian groups Z mod Pi to some power Ki Z. And I goes from 1 to capital N. For some N, some non-negative integer N, and capital is also a non-negative integer, and let's say that PIs in Z are prime numbers. And particular case number 2, which is probably even more exciting, it is the proof that Jordan normal form exists. So if K is an algebraically closed field, which means that any polynomial has a root, and V is a finite dimensional K vector space. And we take a linear operator phi from V to V. Then I claim that we can choose a basis of V such that the matrix A of the linear operator phi is in the Jordan normal form. Which means that A is equal to this block matrix lambda 1 through lambda n. So these are some blocks on the diagonal. Everything else is 0. And each Jordan block is of the form lambda I is on the diagonal. There are ones off the diagonal and 0 everywhere else. So for example, these blocks can be just 1 by 1 matrices consisting of one element lambda I. Okay, let us think about this situation. So in part 1 of our considerations, let's say that K is any field And phi is a linear operator from a finite dimensional vector space into itself. Then I introduce the ring R, the ring of polynomials in one variable, kx. It is a Euclidean domain with the Euclidean function the degree. In particular, it is a principal ideal domain. And then I can turn V into an R module as follows. So if f of x is a polynomial and v is a vector in V, then f of x times v, the action of R on V, is defined as plug phi in place of x here and apply the resulting linear operator to V. So for example, if I have x squared plus 5 times V, it will be equal phi squared of V plus 5V. Okay, now I claim that V with this structure of R module is a torsion module. So indeed, if a V had a free part, then note that dimension of R over K is infinite. So then the dimension of V would have been infinite. But V is finite dimensional, and so it cannot contain a copy of R as a submodule. Dimension of V was assumed to be finite dimensional, finite. And so we have no free part in this decomposition, and therefore V is just the torsion part. And as such, it is equal to the direct sum of R mod out by a power of an irreducible polynomial, fi of x to the power ki, for I from 1 to some capital M. And fi's are powers of irreducible polynomial. And so far I haven't used that K is algebraically closed. And now we recall that we started with an algebraically closed field. So let us understand what kind of polynomials fi's can be. So fi of x in Ki join x is irreducible. And I claim that they only can be linear polynomials. So let's see, they cannot be constants because constants are units, and we want irreducible elements to be non-unit. And they cannot be of degree greater than 2, because if the degree of fi is greater than 1, they cannot be of degree greater than 1, because if they are, we know that they have a root, that fi would have a root, and therefore it would be divided by a linear polynomial of the form x minus this root. And so it would not be irreducible. And because K is algebraically closed, all Fi's are of the form x minus lambda I for some constants lambda I in K. And so we have a refinement that V is isomorphic as an R module to the direct sum R mod x minus lambda 1 to the power K1 plus etc. R mod x minus lambda n to the power Kn. And let us analyze each particular summand. So I claim that the basis where the first vector is x minus lambda to the power k minus 1, the second vector is x minus lambda to the power k minus 2, etc. till x minus lambda and finally 1, turns the module, the R module, R mod x minus lambda to the power k into a Jordan block so this thing with respect to the linear operator of multiplying by x. So the operation of multiplying by x can be represented in this basis as lambda 0, 0, 0, then 1 lambda 0, 0, 0, 0, 1 lambda, and all zeros here, until we get 0 here and 1 here. So 0, 0. And let me prove it. So what do I do? I take x and act with x on an element of this quotient module represented by 1. So then it will be the element represented by x, but this is the same as if I write x minus lambda plus lambda. So the last basis vector is transformed into the last but one basis vector plus lambda times the last basis vector. So x minus lambda plus lambda times 1. And so we get that the last basis vector, whose image is written in the last column, is transformed into 1 times the last but one basis vector plus lambda times the last basis vector. Then, more generally, if j is smaller than k minus 1, then when I multiply by x the element x minus lambda to the power j, I get that I can write it as x minus lambda to the power j plus 1, and the correction term is lambda times x minus lambda to the power j. And so x minus lambda to the power j, it is the k minus jth basis vector. And so for the jth column, we again got that when we multiply it by x, we multiply the k minus jth basis vector by lambda here, and add 1 times the previous basis vector. And so we get the jth column. And now onto the first column. So x applied to the first basis vector, x minus lambda to the power k minus 1, it is equal to, so the formula still holds, the formula here still holds, it's minus lambda to the power k plus lambda x minus lambda to the power k minus 1. But in this case, x minus lambda to the power k is equal to 0, because we are modding out by the ideal generated by this element. And so we just get that x acts on the first basis vector by multiplying it by the scalar lambda. So this is how we prove the form of the first basis vector. Okay, and so I proved the claim. And now recall that I defined the action of R on V in such a way that X acts on V by applying phi to V. So this basis translates into a basis of V that gives, for which the matrix of phi is written of Jordan blocks. So if we take all these bases for each of the summands and translate them under the isomorphism into a basis of V, we will get the basis of V for which phi is written as a matrix consisting of Jordan blocks.